Yes, I see Chris is ready for his talk, I think.
I am, yes.
Very good. So the next speaker is Chris Heunen from the University of Edinburgh, and he will speak about the Sheaf representation of monoidal categories. Please, Chris.
Thank you, Marino. First of all, let me start by thanking the organizers. So 2 years ago, I had the pleasure of organizing CT, and I think of it as a pleasure, but it was sometimes a mixed blessing. But this year, I can't imagine it's a pleasure at all, and I'm very glad that they are making everything work. The second thing I would like to say is I would like to really thank Ruben van Bell, who wanted to swap talks with me because I couldn't on Saturday on my original slot. So whatever you do, please go and attend Ruben's talk. I've seen parts of it before. It's great stuff. Make sure you don't miss it. So having said that, let me start talking about what the talk is about. I want to talk to you about a theorem that gives a sheaf representation for monoidal categories, and that's joint work with Rui Suarez Barbosa. And it falls in a program that I've been calling tensor topology that J.S. Bacoleme mentioned on Tuesday afternoon, and that's not to be confused with monoidal topology that Walter Tholen will be talking about on Saturday, I think. So what is this theorem about? So the slogan is that categories should be nice and easy. So for example, if we think about everybody's favorite category, that of vector spaces, that's a monoidal category, but that's not all there is to say about vector spaces, of course. So for example, vect times vect, the product of vector spaces with itself, is also a monoidal category. But vect on its own is easier in a sense because it does not decompose as a product. So the theorem I'd like to show you will be about how nice enough categories are always easy in that shape. So there will be one theorem and one corollary. The theorem will say that any nice enough monoidal category is a sheaf of these easy ones. And the corollary will say that any monoidal category whatsoever embeds into one of these nice ones. So any monoidal category can hence be represented as a subcategory of a sheaf of these easy ones. That's the very rough overview. So let me start again with this example, vect times vect. So we can write it as a product of vect, two copies of vect. So the product is indexed over a topological space, if you like, with 2 points. And that category is decomposable. It is a product precisely because this topological space is a disjoint union of these 2 points. So if I want to start investigating how to decompose an arbitrary monoidal category into a sheaf over some base space of other monoidal categories, I have to first reconstruct these opens of that base space. What I'm going to use is something called central idempotents. I'll explain in a minute what they are, but I can tell you now what it means for a monoidal category to be nice, as I was saying in the previous slide. Nice means that these central idempotents behave well. I'm going to have two versions of nice. The sort of weakly nice version is called stiff, and that means these central idempotents form a semilattice that's respected by the tensor product. And the nicer version of nice I'll call having universal joins, means that it's not just a semilattice, but a complete lattice respected by joins, by tensor products. So there's two versions of when a category is nice, and it basically means that these central idempotents behave well. And also I'm going to say a category is easy when these central idempotents are, in a sense, as simple as possible. To be precise, I'll call a category local or sublocal when any cover contains the open that is covered. So if I think about a topological space, for example, this 2-point space in the example of vector spaces, topological space is local exactly when any net converges to a single focal point. So this focal point sort of determines everything there is to say about the space. In a sense, the space is as close to a singleton space as possible. So in that sense, it's a very easy space. And if you think about these spaces logically, then being sublocal is the same as having the disjunction property or the existence property, which means if a disjunction is true, then either of the summons is true. So if A or B, then A must be true or B must be true. Okay, so let me go a bit more precise by what I mean by sheaf, just to make sure we're all on the same page. I'm going to assume that people know what sheaves are, because usually people think about set value sheaves, and I want to be talking about sheaves with values in monoidal categories. So the rough idea of a sheaf, of course, is you have some basic space, topological space, And sheaf is a functor from a frame of opens to some codomain. In this case, I'm going to take monoidal categories. So to any open of the space U, the sheaf assigns some object of that codomain, which is usually sets, such that they paste together in a unique way, sort of the elements of that set. But how do I phrase that if the sheaf does not take values in set? Well, it turns out you can phrase that another way, this sheaf condition. You can say that this diagram here is an equalizer. So let's very quickly look at this diagram a tiny bit. The thing in the middle is a product of all the local sections, the sets of local sections, the objects of local sections. So you're looking at all local sections, and what is being equalized, these two maps, it's saying exactly that they are pairwise compatible in the overlap. So if you take the equalizer, you end up with all families of local sections that are pairwise compatible. And I demand that this equalizer is equal to the value of the sheaf at the union. So saying that this thing is an equalizer means that global sections are exactly the same as families of local sections that are compatible. So in this sense, I'm going to be talking about sheaves, continuous functors from the frame of opens opposite to the category of monoidal categories. And when I say a sheaf of local something something, I'm going to mean that the stalks of the sheaf are local. So not if you have an open of the base space, for example, U, then the sheaf assigns a set or an object of local sections FU to it. If you take U smaller and smaller and smaller neighborhoods of a point, and you take the co-limit of all these objects of local sections, you end up with what's called a stalk. So when I say things like a sheaf of local rings, I mean a sheaf whose local sections are all rings, but whose stalks are not just rings, but actual local rings. Right? So the property sheaf of something something means the stalks have that property. Now, there's a number of results in the literature of the type of theorem I'm talking about that represents some sort of algebraic object as global sections of some sheaf. For example, I'm going to mention three of them. For example, a Boolean algebra by Stone's theorem, you can think about as a global sections of a continuous field of sets, if you like, or in other words, global sections of a sheaf of spaces where all the spaces only have two elements. So all the stalks sort of have two elements. You take global sections of those. Then maybe the original, I'm not really sure about the history, to be honest, but one of the earliest or the most well-known maybe sheaf representation of this type is, I think, due to Grothendieck, but might be going further back, as if you start with a ring, you can take its Zariski spectrum as a base space, make a structure sheaf over that of rings, and the stalks will be local rings. So any ring can be represented as the global sections of a sheaf of local rings. And maybe one that people here are very familiar with is if you start with a topos, you can always represent a topos, any topos whatsoever, as a category of global sections of a sheaf of local toposes. And this is due to, for example, Moerdijk and Lambek and Audi. So I'm going to talk about a theorem that generalizes all three of these things. And the theorem says that any monoidal category with universal joins, that is one of the nicety conditions, is equivalent to a category of global section of a sheaf of local monoidal categories. So any monoidal category I can represent as a sheaf of local ones. And then the corollary I mentioned is if you start with a stiff monoidal category, which is a very weak kind of nice, basically any monoidal category we know is stiff, it always embeds into such a thing. So any stiff monoidal category we can then represent as global sections of a sheaf. Okay, that's the context. Now let me dive into some of the details so you don't go away empty-handed. So I promise you to talk about these central idempotents. If you start with the ordinary category of sheaves, set value sheaves over an ordinary topological space X, it turns out that I can reconstruct the opens of X as these central idempotents. So what are they? They are morphisms into the tensor unit, little morphisms little u from big U to I into the tensor unit. I'm going to ask that they come with the half braiding, so a natural transformation of this kind satisfying some axioms. And this is what the central idempotent means. If you start with a monoidal category, you can take its Drinfeld center. I want the morphism to live in there. So that means it comes with this half braiding. I have to be able to swap the object U with any other object. And the idempotent bit of central idempotent, I mean that the object tensor itself, I want it to be isomorphic to the object itself again. And not just any isomorphism, I want the canonical morphism to be invertible. Namely, if I leave one of the copies of U alone and act with my morphism on the other one. Right, so those are the three properties. In terms of string diagrams, that means you have a morphism from U to the tensor unit that you're able to swap with any other object, and that such that if you go from U times U to U, that thing has an inverse, which means it pictures these things. And it turns out that this property of the inverse, of that being the inverse to this, you can equivalently say as the half braiding at U. If I swap U with itself, that's the same as doing nothing. U just stays put. Right, so that's what it means to be central idempotent. That's the definition. Now, JS was talking on Tuesday about subunits, which is a very similar kind of thing as this, except for that definition, there was the condition that this morphism is monic, and it only holds in braided monoidal categories. So this definition holds in arbitrary monoidal categories. You don't need a braiding at all. That's what this half braiding is for. And it turns out that the monic condition you don't need. It's equivalently stated by this thing. So in the category of sheaves over a space, set value sheaves over a space, for example, these things are exactly the subterminal objects. And in fact, in any Cartesian category, these central idempotents are exactly the subterminal objects. For some other examples, if you start with a semilattice, you can regard that as a monoidal category. Then any element whatsoever of a semilattice will be a central idempotent. So specifically, if you start with a frame of opens of a topological space, any object will be a central idempotent. If you start with a quantile, which is sort of a non-commutative frame, if you like, the central idempotents will form the largest subframe. It's the adjoint to the inclusion of frames into quantiles. If you look at the category of modules over a ring that is commutative but possibly non-unital, then if you look at what the central idempotents are, they turn out to be idempotent ideals, in the sense that they correspond to ideals of the ring that are idempotent in the sense of multiplication of ideals. This is a very interesting example I want to point out. If you start with a bi-algebra over a field, could be a Hopf algebra, does not have to be commutative, does not have to be unital. You start with a bi-algebra, you look at modules over that bi-algebra, that's a monoidal category. You can look at its central idempotents. What are they? They turn out to be exactly the central idempotent elements of the bi-algebra. So that means that the theorem I'll be showing you in 5 minutes says that any module over a bi-algebra I can regard that as consisting of global sections of a sheaf of local such things. So in a sense, that gives a sort of decomposition theorem for non-unital, non-commutative bi-algebras over its central idempotents that I'm not sure I've seen in the literature, so I'm interested in what people might have to say about that. Just to finish my list of examples, those are all sort of algebraic examples. There's also more analytic examples. You can take not just modules. If you start with a locally compact Hausdorff space X, you can look at C naught of X, the values the continuous complex valued functions that vanish at infinity. That's a ring, as even a C-star algebra. You can look at modules over that ring, and you can in fact look at Hilbert modules over that ring, so sort of modules with an inner product in which it's complete. This is not an abelian category or anything of the sort, but the opens of X still correspond to the central idempotents of that category. And just to give an example of a category that's not even braided, if you take any category C and look at endofunctors on C, that's monoidal. But the central idempotents, there's only the trivial one. All right, that's the list of examples. Let's push on. So the central idempotents in any monoidal category whatsoever always form a semi-lattice with the usual ordering of sub-objects over here. So U is below V if and only if U factors through V, or equivalently if sort of U tensor V is equal to U. And now I can be precise about what I mean by these nicety conditions. The weakest one, stiffness, I mean that this equation here is a pullback. Having universal finite joins, that means I'm going to ask that the central idempotents form not just a semi-lattice, but a distributive lattice, that this diagram is both a pullback and a push out, and that there's an object 0 such that A tensor 0 is isomorphic to 0. And that's sort of the nullary and the binary joins, if you like. And this condition that this is a pullback and a push out asks that these joins cooperate with the tensor product nicely. And then, of course, you can also have the infinitary version of that, where you ask that all joins of central idempotents exist, so that they form a frame, and that this thing is not a pullback and push out, but a colimit. Right, so now we're in a position to state the corollary that I was talking about, this embedding. If you start with a stiff monoidal category, that's sort of a very weakly nice one, and all categories I know are stiff, all monoidal categories I know are stiff, I can always embed it into one that is nice in the strong sense, in the sense that it has these universal joins. I can formally add joins of central idempotents in a free way. So that means I can build this category D of C with a strong monoidal embedding of C into D of C, such that if you have any functor out of C that is lax monoidal and preserves these central idempotents in this sense, then that will factor through D of C by a functor that doesn't just preserve central idempotents and tensor products, but also preserves these new joins that we added. So you can freely add joins of opens, if you like, to a monoidal category. And then in the last 3-4 minutes, I'd like to get to the actual construction of the theorem, of the sheaf in the theorem. And I'll just show you the definition. I'm not going to go into any sort of proofs. So as the base space that the sheaf is going to be based on, the sheaf category is going to be based on, we're going to take this semi-lattice or even frame of central idempotents, and we're going to take its Zariski spectrum. So that means we're sort of formally, if the thing is a frame already, we're formally just going to add points to it in the sense of completely prime filters. So if you think about a topological space and loads of opens in it, how could you model a point? Well, you take the neighborhood of all its, the family of all its neighborhoods that get smaller and smaller and smaller and sort of converge to the point. Those things are completely prime filters, and together they form a space called the Zariski spectrum. So that's going to be my base space. Then I have to tell you what the sheaf does to an open, and it's good enough to say what it does to a basic open, to one of these central idempotents. And it's going to be a monoidal category value sheaf, remember. So I have to tell you, if you give me a central idempotent U, I have to assign to that a monoidal category that I'll call C restricted to U. In the Cartesian case, the thing I'm going to describe is actually equivalent to the slice category over U, as we know from Topos theory, for example. The objects are going to be the exact same thing as in the original category C, but the morphisms from A to B, I'm going to take morphisms from A tensor U to B in the original thing. So that's sort of, you take all the maps from A to B, but you restrict them to U first. And then you can compose these things because I can first copy the U and then sort of use both copies to restrict both F and G. Same thing for taking tensor products of morphisms. You just copy the U, move them around using the braiding and put everything in the right slots. Turns out to be a well-defined monoidal category and turns out to do the job. Because now you can compute what the stalks are. It's a bit of a computation, but you can do it. It looks as follows. The objects are still going to be the same thing as in the base category. Morphisms are again going to be maps from A times U to B, but now U is not fixed. U is any open that contains the point at which we're taking the stalk. And I'm going to identify two such things, two such maps, when they agree on some V in the intersection of U and U prime. So that's sort of generalizing the definition of germ to monoidal categories. You're saying that two Local sections are the same at a point when there is a tiny, tiny neighborhood in which they're the same. And again, you can compose them as before. So you can compute the stalks, they turn out to be this, and they turn out to be sublocal. You can just prove that. And that proves the theorem. Isn't it great? So what I've showed you is that if you start with a stiff monoidal category, you can always add universal finite joins to it. And once you've done that, the thing is always equivalent to, and this is a whole mouthful, I'll say it again, the category of global sections of a sheaf of sublocal monoidal categories. You can choose whether you want finite or infinite here. So some applications of this to finish off. This captures the sheaf representation theorem for topuses as a special case that I mentioned earlier by Lambach and Moerdijk and Orde and others. But it also applies directly now to things that are not topuses. For example, stone duality for Boolean algebras. For example, Takahashi's theorem about Hilbert modules that you can always represent as a continuous field of Hilbert spaces. And the Peirce spectrum of a module over a commutative ring. So those things you can now capture directly, not just by analogy. And then to finish off, let me take one more minute, because there's some nice preservation properties in this sheaf construction. If the original category C has a certain property, then both the local sections and the stalks will, in most cases, inherit that property. So for example, if the original is closed, then the smaller version and the stalks will be closed. Now that's something you know from the Cartesian case maybe already, but there's also things that are purely specific to the monoidal case. For example, you can have a traced monoidal category, and that implies that both the local section and the stalks will be traced. It could be that your category is compact in the sense that every object has a dual object, it's rigid. Then both the local section and the stalks will have that. It could be that your original category is Boolean in the sense that the central idempotents have complements like this. Then the local sections will be Boolean too, and so will the stalks. And in fact, the stalks will be 2-valued, so there will be exactly 2 central idempotents. Limits are inherited, any limits, which is maybe expected if you think about slice categories. Co-limits are a bit more tricky. You have to ask that the co-limits are preserved by tensoring with a fixed central idempotent, so they're sort of flat, if you like, or projective. If the original category is projectively co-complete in that sense, then the local sections will inherit that. For the stalks, I can only prove it for finitely co-complete. But in general, if the original category has nice properties, then so will all the stalks and all the local sections. I'll just flash this at you before stopping. You can make all of this functorial. So what I've described is a mapping that takes an object of the category of monoidal categories with the right types of morphisms and assigns to it a sheaf. And if you, of monoidal categories, and if you take the right kinds of morphisms between sheaves, then this becomes an equivalence, a dual equivalence of categories. One thing to note here is that the sheaves that I've described, these C restrict to U, are not just any sheaves, they are what's called flabby, in the sense that if I have a local section over U, there's always a canonical way to extend it to a global section over all of X. That's basically what this tensoring by U did. And that's where I want to stop. So let me summarize. I've talked to you about a theorem that takes a monoidal category and represents it as a category of global sections of a sheaf. And one way to think about this is that it clearly separates spatial directions in the sense of the space X and sort of temporal directions in the sense of composition and even maybe tensor product in all the small categories CU. It captures more examples than we had before, and the proof is entirely concrete. There's no need for going to stacks at any point. There are some interesting questions that we want to look into next. For example, the sheaf representation for topuses said something about completeness and coherence theorems for intuitionistic higher order logic. You would expect that the same thing happens here with some sort of linear logic, and we're looking into that. And some other interesting questions. So let me just skip those and let me leave you with some references, and thank you for your attention. Thank you very much.
Many thanks, Chris, for this interesting talk. Other questions? in the yes, one. Steph Canapé.
Okay, just a remark. So your sheaves are always on the open sets of topological spaces.
That's right, yes.
One thing that might be looked at is at Grothendieck topologies. You can define sheaves on that also, and that has been done in algebraic geometry. And perhaps this could be generalized.
Mm-hmm. Yeah, that's a good question. One that I've wondered about but haven't dared to attack yet. You could talk about sites. That's completely right. I guess the question then becomes, what happens to the tensor product of the site?
Okay.
Thank you. There is one question online.
Hi there, very interesting talk. You mentioned stacks right at the very end. This was something that was in the back of my mind throughout the talk. You said something like there's no need to go to stacks. I guess for me, the question would be reversed. Why can you get away with using sheaves? Is it the case that the sheaves or stacks that come up just happen to naturally be sheaves, or have you done some technical rectification construction just to remain in the world of sheaves? Or what would you say is the point?
So we've studied the topos representation proofs. For example, the one by Botte is the latest one, the latest write-up of it. And the way he proves it is he uses a very general, he appeals to some sort of equivalence theorem for stacks, that any stack of such and such a shape is a sheaf. I think the way we get away with just staying with sheaves is by doing everything very concretely. So for example, when I showed you this category, you can just define what it is. There's nothing up to equivalence. If you work with slice categories, for example, as is usual in the proofs of in the topos case, this is only up to equivalence. You have to choose products and these sort of things. I think that's where it helps to be more concrete, right? To have a definite tensor product, you have a canonical choice and you can use it. I'm not sure that's the right answer, but I think that definitely plays into it.
That's interesting.
One additional thing I could say is that you have to be very careful about C restricted to the bottom element, because that's the only place where it's really an equivalence rather than an isomorphism, and we have to work around that. But yeah, for details, I'll have to refer you to the paper. Sorry, it's hard to put these things into words.
So thank you very much, Chris, again. We have a half an hour break and we resume at 11.